we're going to kind of look at an introduction to this, and then we've got an activity we're going to start and see how far we can get. We may not get all the way there. Even though if we don't, that might be good, so I can bring the good toilet paper from the house, because this toilet paper is not good. You can't see the squares good. Okay. It is 2-ply, but I mean but it's not good 2-ply. It is not good 2-ply. So we're gonna have to see what we can do with that. Yeah, it would be better to have some premium toilet paper for this particular. But I'll bring some good TP from the house if we don't get to the toilet paper part of this. If I can remember. Problem is all right. So, all right. The graph to the left shows the velocity of a car carrying a crash dummy. What is the velocity of the car at t equals 3 seconds? Okay, so this is the graph of velocity. So when they ask us for velocity at t equals 3, we are just finding the coordinates of that point, right? So v of 3 would equal 16 feet per second. Okay, the next thing it asks us for is the acceleration. Okay, acceleration would be the derivative of velocity, which is our slope of this graph. And 1, 2, 3. Oh, we got to be careful. We got to make. Are those worth 1 unit? They are. Okay. 1, 2, 3, 4. 3 over 4. No, these are 1 units. 3 feet per second. Does that look right? I think so. 3. Yeah. So acceleration would be constant. It wouldn't matter what time, right? Because we have a straight line with a constant slope here. So that would be 3 feet per second. I'm going to write this way per second, or you can do feet per second squared. When we're talking about units, remember this. When we're doing slope, it is change in y over change in x. So your units, your y units are feet per second, and then your x units are seconds. So that's where this other extra seconds goes from. Change in y is in feet per second. Change in x is seconds. Okay, so using the logic that we used on the warm-up, right? On the warm-up, we could reason through it pretty well. This does not have a constant velocity. It is not like the last problem where we were going 40 feet per second for 5 seconds. 40 times 5 is going to give us, 40 times 5 would give us that 200, right? But if I want to know how far the car travels in the first 7 seconds, then if I look at where time equals 0 up to where time equals 7, if I could find the area underneath this curve right here, if I can find that area, I'm doing feet per second on my y times seconds on my x, which causes the seconds to cancel, which gives you the number of feet that have been traveled. So that area under the curve gives us the distance that has been traveled. And so, thankfully, this is something we can figure out because we have shapes we can use here, right? So, it's up to you how you want to do it. To do it all in one, this is a trapezoid that you have here. Area of a trapezoid is going to be 1/2 height times base 1 plus base 2. So if you do it that way, the length of this side right here is 7. The length of this side right here is 28. And the length of this side right here is 7. Right? So it's kind of turned on its side. The height would be 7, this 7 right here. And then the bases are the parallel sides. So it would be 1/2 times 7 times 7 plus 28. And 7 plus 28 would give us, so we have 7/2 times 7 plus 28 is going to give us 35. And 35 times 7 is going to be 210 plus 35, 245 over 2. Somebody might need to check me with a calculator here. 122.5. Okay, you don't have to use area of a trapezoid. You could take this right here, make it a triangle and a rectangle and add those together. That's fine. You know, it doesn't matter exactly how you do that. There, you can do it either way. It's okay. But that'll give us our area, which will give us the distance, which is pretty cool. Because the problem, if you know you have a constant acceleration of 3 feet per second, and the velocity at t equals 0 is 7 feet per second, then you can figure out how far that car would go in the first 7 seconds. So, you know, that's more difficult to do than just a constant rate of change. Constant rate of change is pretty easy for that. Okay, questions? Now, this is how far the car traveled. We don't know where it started, right? It didn't tell us where our starting point is. We just know in that 7 seconds that it traveled 122.5 feet. So if it started at 0, then that's where its position would be. If it started somewhere else, if it was already 50 feet down the track, then we'd have to add that to what we had to find position. But this gives us, you can see the title of these notes are Integration and Accumulation of Change. It gives us the change that has occurred in that position. Okay, questions? All right, the graph to the right shows the rate at which the amount of water in a tank changes after t minutes. Okay, so again, we're looking at a rate here. At what rate is the amount of water in the tank changing at t equals 3 minutes? What do you guys think on that one? Okay, we're just looking at this point right here. Okay, and this is the rate of change, and it's asking for the rate of change. So it's just 6 gallons per minute. Okay. At what rate is the amount of water in the tank changing at t equals 6 minutes? Okay. Okay, what's it asking us for? It's just asking for the rate of change. What is this the graph of? This is the graph of rate of change. The answer right there is 8. If they asked for the rate that the rate of change was changing, then we wouldn't be able to answer that because we've got a sharp turn in the graph and we couldn't tell what the slope is. But this just asks for at what rate is the amount of the water in the tank changing. This is the rate of change of the amount of water in the tank. So we're just reading off from the y-axis here. That would be 8 right there. So it's okay that there is a sharp turn there because it's not asking us for derivative. If it asked us for derivative, it would matter that there's a sharp turn there, but it's not. Does the amount of water in the tank ever decrease? Okay. Connor says no. What about over here, Connor? This looks like it's decreasing to me. Okay, because it's asking us about the amount of water, right? Is this the graph of the amount of water? It is not. So when we see this decrease, it doesn't mean the amount of water is decreasing because this is not the graph for the amount of water. So Connor, how can we know that our amount of water is still increasing? We're above the x-axis. We still have a positive rate of change here, which means like right here at 10, the water is still being added to the tank at a rate of 5 gallons per minute. It's filling up slower than it was up here, but it's still filling up, right? We're still adding water to the tank. So the answer for this would be no, the rate of change is always positive. So for us to see like a leak in the tank, for water to be drained from the tank, we'd have to see this line drop below the x-axis. All right. For D, it says, is the rate of change of the amount of water in the tank increasing or decreasing at t equals 5 minutes? Okay, a little bit of a trick question in its wording, right? We're looking at rate of change. We're looking at this graph. Is that graph increasing or decreasing at 5? Neither one, right? It's just constant. It's just standing still. So we would say neither rate of change is constant. All right. E is the thing we're focusing in on, right? How much water was added to the tank over the first 10 minutes? So if I want to know, this is my rate of change, if I want to know the amount of water that was added, I can do the area under this curve, right? So there's a lot of different ways you could split this up. I think I'm going to do it like this. I'm going to go from 0 to 4 right here. Then we'll make myself a rectangle right here. And then I'll have a trapezoid over here. Or I could just do, I might even do that, right? However you want to split it up, you just need to break this into shapes you can find the area of. So for this triangle right here, we're just doing 1/2 times 4 times 8, right? And that's going to give us 16 gallons for that section. For this section right here, it's just a rectangle, so it would be 2 times 8. So we'll also get 16 right here. This section right here, we got 4 times 5, so we got 20. And then up here, we got 1/2 times 4 times 3. So half of 12, which will give us 6. And so if we add all of those together, 16 plus 16 plus 20 plus 6, we're going to get, let's see, 32, 52, 58. So 58 gallons. Okay, so that's the amount of water that was added to the tank. If there were already 100 gallons in the tank, then it'd be 158 gallons total if they asked us for the amount. So we just know this much was added. If the tank was empty when we started, then there's only going to be 58 gallons in the tank. It just depends on what information you have, and that was not given to us. Okay, questions? So, similar idea as the velocity, but a different application. We're not really dealing with velocity here, right? We're dealing with rate of change of something different. Okay, so a drag car travels down a track. Selected speeds of the drag car are given in the table below. And it's going to ask us several different things, and I put a graph over here so that we could graph these to kind of help us see if we wanted to. All right, so first of all, it asked me for average acceleration of the car for the 2.5 seconds. So, what is acceleration? It is our derivative of velocity. Since we are not looking at derivative at a specific point, we're looking at over an interval from 0 to 2.5 seconds. What do I have to do to find that rate? Good. Slope formula, y2 minus y1 over x2 minus x1. So I would do 145 minus 0 over 2.5 minus 0. So 145 over 2.5. And let's just grab the calculator. What is it? 58. What would my units on that be? Okay, feet per second, which is perfectly okay to use 58 feet per second squared. You'll see. You could see either. Which is, I would imagine that they have a U.S. version of the test and then the test that they give internationally. I would imagine on the international version that they don't use imperial units very much, but I'm pretty sure I have seen imperial units on, let me go back and look. I'm pretty sure they use imperial units for this, I think. I doubt they do on that. It typically, like, they're not usually going to give you something where it's you're going to need to convert from feet to inches or something like that where it would really matter. Okay. B asks us to estimate the acceleration of the car at 0.75 seconds. Okay. What should we do there? Can we know the acceleration exactly at 0.75? We cannot, because it's not asking for an average acceleration. We want like instantaneous rate of change acceleration. All we have is a table, so the best we can get is to use the points close to it and do the slope formula like we just did. So at 0.75, that would fall right here between 0.1 and 1. So we would do 110 minus 60 over 1 minus 0.5, which would give us 40 over 0.5, which would give us 80 feet per second, or feet per second squared. Yes, sorry. I was looking at that as 100, which makes it 100. All right. Estimate the distance that the car traveled in the 2.5 seconds. All right, now this is going to be, okay? This is going to be different. This is why I put the graph here. Let's put the graph. Let's graph these points. So 0.5, 60, 1, 110, 1.5, 130, 2, 140, 2.5, 145. So we don't know that we have straight lines here, but the best we can do is put some straight lines there, right? So we've got this graph. All right. So if we want to know the distance the car traveled, our seconds is on our x-axis, our feet per second is here on the y-axis. If we can find the area underneath the curve, that would give us the distance traveled. But we just have like certain points. So this is not going to be exact, it's going to be estimate. This is what I'm going to do. I'm going to draw some lines right here. Okay. Can we find the area of each one of these sections? We can. With those straight lines, we can. Right now, the actual line might be curved. We don't know what's happening exactly. It probably is curved. But this is going to be a decent estimate of what is happening here. So if we look at this, we need to find the area of all 4 of these sections. So let's do this. Paul and Zach, you find the area of section 1 right here. Cade and Bo, you guys do 2. Hallie and Grace, you guys do 3. Braden and Wesley, you guys do section 4. And I'm going to have all 4 of you guys do section 5 right there. Find the area of that section. Yep, assume that's a straight line right there. So you can either use a trapezoid or a triangle or however you want to do it here. And I'm just splitting up the labor here so that it is quicker. The bases of a trapezoid are the parallel sides. So it's almost like your B1 and your B2 are going to be your vertical sides here. So it's almost like you want to call that height the width because it's going to be on that x-axis there for this. Yeah.
How do you do it with this?
I do not know.
It's like you can calculate this.
What are you want to do, like a line of best fit or a...
Like try to find a relative formula
for those. I think it's going to be for 2 variable stats. No, that's not right.
Yeah.
Oh, 0.5, I did times 4.
Try to calculate like formula based on the values.
I'll have to look into it, Connor, because
Yeah.
actually it's going to be right here, regressions. There you go. So it's F4, and then regressions, and then you'd have to pick which one you want to do there.
It looks like
Although it'd be like your L1 and L2. I think we don't. like, what you're doing is interesting to do, but would never be what you would do on an AP exam, so, like, they wouldn't count it, so,
Like, how do you put?
you do it less 1 and less 2, so, which one were you going to do?
I can't remember why.
Okay. Let's see if it just works with 1 and 2. How do you tell it list? I mean, you can probably just type in list.
So is it then
I mean, other than typing in the word list, I'm not sure. I think you gotta type in list 1 and list 2. Alright. Okay. Alright. Up here, what did you guys get, Paul and Zach, for your section? 15 feet. Okay, Cade? 42 and a half feet. Okay. Grace? 60 feet. Wesley? Okay. And then over here for section 5. Okay, I'm not double checking all of these, but they seem reasonable because they should be getting larger, right? So I'm going to trust that you guys found that area correctly. So if we add all of those together, 15 plus 42.5 plus 60 plus 67.5 plus 71, we will get 256.25 feet. So I split up the labor on that because we had 5 different sections we had to find the area of, which took a little bit longer if we all did it, but this would be our estimate. Now the actual graph, is probably more of a smooth curve that looks something like this, which would be close. It works when you type in less 1, less 2. Yeah. If it is a smooth curve, we're going to learn about how to do that, but not today. All right. There's a way. Okay. All right. This problem is a crazy problem because in January of 2020, Coach Wood comes down my hallway and asks me things like how many Coronas you got to drink to get the coronavirus. This is January 2020. We're still in school, right? He asked me these questions. In China, they're tracking this stuff. Like, it's in the news, but it's only in China right now. So I thought, this is interesting. Let's make a problem about coronavirus. I made this problem about coronavirus in January or February. I was pulling these numbers. So we're probably like February 4th. I'm doing this problem, which is also good because it means we're ahead of where we were then, right? Because I was pulling numbers from February 4th. So I'm pulling all of this data on coronavirus numbers when it's still in China, and I think it's never going to be a problem around here. 3 months later, we get kicked out of school, can't come back for the rest of the year, have to come back with masks. The whole world is turned upside down. So, back whenever Coach Wood and I were joking about this, and, we're like, oh, it shouldn't be a big deal, I made up this problem. And I'll leave it in here because I think it's interesting that I did that. So, these are the deaths per day. Notice how small these numbers are. On these dates in the year 2020. Well, the dates are backwards, so it is getting larger. But still, we were talking 66. If it had stayed at 66, probably the world would have never cared that much about the coronavirus, right? Because, you know, we were in the thousands just in our country alone. So by the time it blew up. This was very beginning in China before anybody knew much about what this was. Like, at this time, it was only in China. Or at least, we only knew it was in China. Right? Did you do it that way? Yeah. 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 Right. Yeah. Okay. So, from January 23rd to January 29th, the number of daily deaths increased at a rate of. Okay? So, from the 23rd to the 29th, number of daily deaths increased at a rate of. So, we're looking at daily deaths, which is what we're looking at, right? And we're looking at the rate that it is changing. So we're looking for the rate of this table, right? So from the 29th to the 23rd, we're looking for the rate of what we're looking at. We're looking for derivative. We're looking for slope. We're going to use slope formula here. So we would do 38 minus 8 over 29 minus 23. Okay. And that's going to give us 30 over 6. And so we would have 5. And that would be deaths per day per day. Oh, there's something else we need to do. If I'm going to call this 23, and I'm going to call this 26, and I'm going to call this 29, that would make this 30, but there is a January 31st. So January 31st would be 31. February 1st would be 32. February 2nd would be 33. This would be 35. So let's use days. Well, okay. So at this point, it's going up about 5 deaths per day per day. So we're increasing here by that amount. From January 30th to February 4th, the number of daily deaths increased at a rate of. So from the 30th to the 4th, if we're looking at that rate, we've got 35, I'm sorry, those are my X's, 66 minus 43 over 35 minus 30. And that is going to give me 23 over 5, which is going to be 4.6 deaths per day per day. At this point, I say, oh, it is increasing, but at least it's, acceleration is not as much as it was. So maybe it's going to slow down and not take off. That's what 2020 Miss Hyatt said at this point, who knew nothing, obviously, about what was going to happen. I don't think anybody really knew. All right, so if we have this information, it asks us to estimate the total number of deaths due to the coronavirus between January 23rd and February 4th. So let's do like we did on the last problem, and let's graph, although, given my graph, I need to rethink what I was doing here. let's make this 0. So 23, 24, 25, 20. So this would be 3. So subtract 23 here. This is 6. This is 7. This is 10. And this is 12. Got that right? Yeah, it'd be 12 days. Okay. So if we graph our points, we got 0, 8. We've got 3, 24. We've got 6, 38. We've got make it a little bit lower right there. This one. So if we're at 23, 24 would be like just a little bit lower right there. And 6, 38 would be a little bit higher right here. Obviously, this doesn't have to be precise. 7, 43, 7, 43. And 10, 58, 10, 58, and 12, 66. Okay, it looks pretty linear. It's not exactly, I know it's not exactly linear, because whenever I did A and B right here, I didn't get the exact, like I didn't get the same number, although these are pretty close to each other. But it's pretty close to linear here. But to get the most precise prediction, I would need to split this into sections like I did before. Now, what's different about my sections this time than it was on the last problem? There is no triangle for the first part, so they're all trapezoids. Also, on the last problem, what do you see about all of your intervals? What's the width of all of them? They're all the same. Is that the case over here? It is not. So when you're finding the area of these, the interval of each of those are going to be different. So let's do the same again. We'll do section 1, 2, 3, 4, and 5. Find your area of your section. Just do the same one you had. 1, 2, 3, 4, 5. There. Yeah, it would be, you're on section 3, right? Yeah, the height of the trapezoid would be 1 if you do it with that. Because it's really like you're thinking of it like the height is really sort of the width. Because the trapezoid, the parallel sides are your bases. All right.
I cannot tell where the dots are.
Yeah, so what you want to do is you can use your table to know. So like, you know the width would be 1. That base right there, that's for 6, right? So the height of this side right here would be 38. And then the height of the other side would be 43. And so if you use those numbers from the table, then you can get the exact. All right, what did you guys get over here for section 1? Okay. Section 2. Okay. 40.5, which we know half is not possible, but mathematically we can do this for like estimates, right? We know in reality that wouldn't be the case, but we may end up with half somewhere else that kind of go together. So, Braden, you're... And 5 over here, 124. Okay, so if we add all those together, we get 457 people. Did you do a regression and integrate? On the AP exam, there would never be one that they want you to do a regression and integrate on.
No, if it's an estimate,
You couldn't get, they wouldn't give you. They are not, they are going to specifically say, like, as we get into this more, you'll see, like, the different types of things. So they are never going to ask you to do that on the AP exam. Although, you know, it is kind of cool to look at. So Connor is finding a regression for these, and then he is integrating because he has put together that if I integrate, it's going to give me that area underneath the curve. So if you find that regression and integrate, it's going to give you an estimate, and that is one way you could approach it, but there would never be one on the AP exam where they want you to do that, and you won't get the, like the way they word the problems, it wouldn't be right to do it that way. But it's kind of cool to look at. Regress means to find an equation that fits those lines. So you did that all the way back in like Math 1 where you did like lines of best fit, where you put in like L1 and L2. Well, you either put in Desmos or L1 and L2 in the calculator, and then you told it to do like Y1 squiggle MX1 plus B. So you get an equation to fit your points. And then integrate is something I haven't taught you yet, but Connor's a step ahead. And integrate and finds the area underneath that curve for you. So it's an approach you could take. But as far as the AP exam goes, and this is also an estimate, so like what you have is an estimate, and what I have here is an estimate. Yeah, so you know, if you were actually doing research on this, then, you know, you would want to look at some different methods and make decisions on what is most accurate to do. You also might have more information, right? At this point, 2020 Miss Hyatt, January 2020 Miss Hyatt said, oh, look, hopefully it stays over there. I think we'll be okay. Don't worry about it too much. It shouldn't bother us. And we went on with our lives for a few more months. Happy as we could be. Until they canceled the ACC tournament. I was like, oh my, things are about to get bad. They do not cancel the ACC tournament. That's serious.